Right. So we are discussing the network models, and in our previous class we have really seen the tree and the spanning tree concepts, and from there now let us move ahead to another concept that is known as the cutsets. So the cutsets is a very important concept that basically a cutset, you can say it is a set of edges in a graph G. If you remove them, then the remaining graph should be disconnected. But the question comes that how many such edges should I remove? You see, an extreme case is you remove all the edges and the graph is disconnected. So, is it a cut set? The answer is no. It should be a minimal set. But then this minimal set is also a something very important to understand. It is minimal set in the sense that a subset of these many edges should not be a cut set. That is the essential idea. So, let us look at some examples to really understand what it exactly means. See, cut sets. Suppose I have a graph of this type. So, this is a graph. Is it all right? So, let us say this is a small graph. So, this is a graph, and this graph has got 4 vertices V1, V2, V3, V4, and there are edges like E1, E2, E3, E4, E5. So, now if you remove, let us say, out of this graph E1, E2 and E3, a set of edges. So, remove these 3 edges. What is the resulting graph? The resulting graph would be V1 would be here, V2, V4 and V3, E4, E5, V2, V4, V3. So, this is the resulting graph because we have removed these 3 edges. So, is it a cut set? Is it a cut set? You see what we have done? We have a graph. From this graph we have removed 3 edges, and this is the resulting graph. Question is it a disconnected graph? Yes. Why? Because V1 is on one side, V2, V3, V4 on the other side, and there is no path from V1 to those edges. So, this is a disconnected graph. So, the question comes that E1, E2, E3, is it a cut set? The answer is no, it is not a cut set. Why it is not a cut set? Because a subset of E1, E2, E3 is a subset of E1, E2, E3, namely E1 and E2 also does the same. Also does the same. Same means what? If you remove, see, look here, remove E1, E2, then what will be the resulting graph? Resulting graph will be this, V1 here, V2, V3, V4 is here, E3, E4, E5. So, this one, is it a disconnected graph? Yes. it is a disconnected graph. So, you see, therefore, you can say that E1 and E2 is a cut set. This is a cut set, but not a cut set. Obviously, we should additionally check that as I remove E1 and E2, is the subset of that also does E1 disconnects the graph? No. E2 disconnects the graph? No. So, E1 and E2 is a cut set. So, that is how you have to understand what is a cut set. So, look at the theory now, that a cut set is a set of edges in a graph G whose removal leaves the graph G disconnected, provided that no proper subset of these edges does the same. So, this point we must recall and remember. You can alternately say it is a minimal set of edges whose removal leaves the graph G disconnected. Is it all right? So, that we must remember. Now, let us look at the same graph once again and find out all the different cut sets. So, we had this graph and we had E1, E2, E3, E4, E5, V1, V2, V3 and V4. So, we had this particular graph, and what are the different cut sets that you can think of? You see, you can, let us look at some cut sets. Suppose, is it a cut set C1? So, C1 is E1, E2, it is a cut set. Already we have seen that. What about this one? Is it a cut set C2? This is C2. C2 is E1, E3, E4. This is also a cut set. Is it a cut set C3? This is also another cut set E4, E5, right. This is also another cut set C4, C4, that is E2, E3, E4 is also a cut set. Like that, we can have this one which may be called C5. So, C5 which is E2, E3, E4, this is also a cut set, right. So, you see, you can still think of some more like E1, E3, E5, is it all right? Maybe I do not know, maybe we have covered more or less all of them. So, there could be C6, C6, this is C6 which is E1, E3, E5 like a cut set. So, you see, we have found out 6 cut sets here, maybe we can find even more cut sets. So, you can see that this is becoming really a rather complex task to identify all the cut sets of a particular graph, right. There could be so many different cut sets that are actually disconnecting a particular graph. So, if you look at the notes once again here, as you can see that in this particular graph, if you have to find all the cut sets, can you think and identify some of them? What about U1, E2? Is it a cut set? Answer is yes, it is a cut set. Can you think of something like E1, E3, E4? Look, if you draw these E1, E3, E4, it separates the graph into two parts, these two vertices on one side, these three on the other side. What about E4, E5, E6 or E4, E5, E7? What about E6 and E7? You see, like that you can find so many different cut sets, and you can look here, some of them are identified here, right. So, cut sets of the graph E1, E2, E1, E3, E4, E1, E3, E5, E6, E1, E3, E5, E7, E2, then E3 and then E4, E2, E3, E5 and E7, then E4, E5, E6, E4, E5, E7 and E6, E7. So, you see like that all the different cut sets one can find out, and question still remains how to find all the cut sets of a graph. As you can see, the process is very cumbersome, and that too just for a very simple graph. Suppose the graph is little more complicated, then what would be the cut sets and how do you find them? It could be much more difficult and involved. Now, let us understand some more important concepts regarding these cut sets and other sort of things. One such concept is called the eccentricity of vertices, right. First of all, we must understand that there is something called distance. Distance is the length of the minimum path. Now, question is that is it a weighted graph or a not a weighted graph? Usually, particularly for communication circuits, sometimes the length is not the important thing, the junctions are more important, how many nodes it pass through, right. So, therefore, the essential idea there is what is the number of edges. So, if it is not a weighted graph, we will mainly think of the number of edges at the distance. So, here that that distance is usually a metric because it is a non-negative thing, it is a symmetrical because C1 to C3 and C3 to C1 both are same, and there should be triangular inequality. That means, if we have C1 to C5, right, should be less than C1 to C5 should be less than C1 to C4 and C4 to C5. So, if you add the distance from C1 to C4 which is 3 and C4 to C5 which is 2, then we get 6, that should be higher than C1 to C2, C3 to C5 which is 4, that is called triangular inequality. So, distance is a metric. So, anything that is a metric has got these three properties, and since distance is a metric, we use that metric to identify some basic ideas. One such idea is an eccentricity of the vertices. Why eccentricity of vertices is so important? Because if you can find out the eccentricity of vertices, we can know the design of the graph can be possible very simply and easily. We will see that little later. So, eccentricity of a vertex V is the distance of the farthest vertex from V. So, what is the eccentricity of C1 then in this tree? What is the farthest vertex? So, we can work that out. Supposing we have a particular tree, let us say suppose this is a tree, say C1, C2, C3, C4, C5, C6, C7. Now, what is C1 to C2? The distance is 1, C1 to C3 2, C1 to C4 2, C1 to C5 3, C1 to C6 3, C1 to C7 4. So, what is the eccentricity of vertex C1? It is 4. Why 4? Because that is the distance of the farthest vertex from C1. So, like this we can actually find out the eccentricity of vertices, and usually the pendant vertices are having higher eccentricity, right. So, can you find out the eccentricity of vertex C3? See C3 would be this side 2, this side 3, this side also 1, 2, 3, 4, right. So, C3 also 4. So, like that we can think of, look at C4. What is the eccentricity of C4? The C4 is eccentricity is this side is 2, this side is 2, this side is 1, this side is 2. So, is there any other vertex which is having lower eccentricity? Let us find them all. So, here let us write down eccentricity and vertex. C1 is, we have found out 4, C2 also 4. What is the eccentricity of C3? C3 would be C3 is, C2 is 3, C2 is 4, because C2 is further from here. What about C4? C4 would be 2, because you see the farthest vertex is only at a distance of 2. What about C5? C5 would be 3. C6 will be 3 again, because from this side. And what about C7? That will be 4. So, you see the least eccentricity is that of C4. And what is the meaning? What is the advantage of that? Then we call it the center, right. So, center is the, and that eccentricity of the center is called the radius of the graph. So, anyhow, these concepts are important really to know that how connected a particular graph is, and what is the farthest vertex from those, and that can be measured in terms of eccentricity. And these eccentricity, once we know, therefore after that we can actually look at two very important concepts. They can be called as edge and vertex connectivity, EC and VC. Edge connectivity EC and the vertex connectivity VC. Let us see how are they important. You see, edge connectivity is the number of edges in the smallest cut set of the graph, right, smallest cut set of the graph. So, let us look at this one. What is, suppose look at this particular slide. Here we have seen the different cut sets. So, what is the smallest cut set, in the sense what is the number of edges in the smallest cut set? Is it all right? The smallest cut set here is number of edges in the smallest cut set. Can you tell me the number? That number would be 2, because 1, 2, there is no other. So, you can see the graph also, you have to remove at least 2 edges from this graph to make the graph disconnected. Is it all right? So, therefore, the edge connectivity of the graph, that is EC, equal to 2. Edge connectivity of the graph is 2. On the other hand, the vertex connectivity, there is, what is the number of vertices whose removal would leave the graph disconnected? How many vertices do I have to remove to leave the remaining graph disconnected? If I remove V1, will the graph be disconnected? Answer is no, because if you leave V1, all the other things are on the other side. Please remember, if I remove V1, the E1 and E2 will go also. Is it all right? Now, if I remove V2, is the remaining graph disconnected? No, because everything else is on the other side. If I remove both V1 and V2, then also no. But if I remove V2 and V4, then the remaining graph will be disconnected. Is it all right? So, interestingly, we can see that vertex connectivity of the graph VC is also 2. Now, question is, between edge connectivity and vertex connectivity, there is a relation, and what is that relation? We shall explore that little later, but at this point of time just remember that edge connectivity of a graph is the removal of the minimum number of edges whose removal will leave the graph disconnected, and same thing about the vertex connectivity. So, here just look at the definitions. EC is the number of edges in the smallest cut set of the graph, minimum number of edges whose removal leaves the graph disconnected. Vertex connectivity, minimum number of vertices whose removal leaves the graph disconnected. All right. So, find the EC and VC of the following two graphs. That is, if I have to find, now look at this tree. Now tell me, what is the EC and VC of this tree? How many edges do I have to remove? Minimum number to make the graph disconnected. Is it 1 only? Because it is a tree, it is a minimally connected graph. There are no circuits. So, removal of any edge will leave the remaining graph disconnected. Is it all right? So, if I remove this particular edge, then C1 will be on the other side. If I remove this edge, then this portion and this portion will be on the two different sides, and there will be two components, right. So, therefore, for a tree the edge connectivity is 1. And what is vertex connectivity? You just remove say C3, look here, the remaining graphs are disconnected. So, you can see that the VC for the tree is also 1. So, EC equal to 1, VC equal to 1. Now, look at this particular graph. What is its EC and VC? How many edges do I have to remove to make the remaining graph disconnected? Is it 2 again? Because if I remove U1 and E2, then remaining graph is disconnected. So, it is 2 here. And what is the vertex connectivity? How many vertex do I have to remove? If I remove only one vertex, just see the graph is still connected, all right. And if I remove 2, let us say these 2 or these 2, then the graph is disconnected. So, in this case also edge connectivity is 2 and vertex connectivity is also 2, all right. Now, question is, do you like higher edge connectivity or lower edge connectivity? Do you want lower values of EC and VC, or you think an higher value is good? Think of a road network. In any road network, there could be some sort of disruption, maybe due to some reason or maybe due to disaster. So, let us assume this road E4 is not working, right. This road is not working. If this road is not working, then what should be, how do I go from say this vertex to this vertex? It is now possible that I can take this path, I can go to here and from here I can go. Is it all right? So, you see, look here, since the vertex here the edge connectivity is 2, then even if a particular edge is removed, you can still go from by using other edges, but vertex connectivity is important too, right. So, suppose these two vertices are removed, then all these edges are gone, all these edges are gone, there will be no path that is available. Is it all right? So, if but suppose this vertex is removed, then what will happen? All these 3 paths are not usable. Look, so vertex is so important, it is just a junction point like a bridge. suppose this particular bridge is not working, right, you cannot go through, the bridge has collapsed, then what will happen? If you have to go from here to here, this path is not usable, or from here to here, this path is not usable, but then you can still use this particular path. So, naturally you can understand that one expects a good value of the edge connectivity and vertex connectivity. It is always better that if you can achieve a higher value of edge connectivity and vertex connectivity, right. So, that is what is required. Now, let us come to another concept, that is about edge connectivity and vertex connectivity, that is called a cut vertex or a cut edge. Look at this graph, if I remove a particular vertex, say this vertex, then the remaining graph is disconnected, or if I remove this edge, then the remaining graph is disconnected. Just imagine that this is, let us say, a particular road, and these are the two cities, and anything happens to this city or this road, all the traffic that goes from here to here will be disrupted. Or imagine that this is one locality and this is another locality, and this is the network or communication connectivity. So, telecommunication link, if there is a failure anywhere between these to this, then entire communication link or either this area or this area will be disrupted, because if the link is coming through that. So, it becomes so vital, and there is no other alternative to really fall back to. So, that is the importance about the cut vertex and cut edge. So, cut vertex is a vertex whose deletion leaves the graph disconnected, right. Similarly, the cut edge concept. Now, look at this is very interesting. What is its edge connectivity? How many edges do I remove to make the graph disconnected? Look, it should be at least 2. So, these 2 if you disconnect, then the graph is disconnected. But what is its vertex connectivity? How many vertex we can remove to really make the graph disconnected? Just see, just 1. Simply if you remove this particular node, then this particular graph is disconnected. So, its vertex connectivity is just 1. So, sometimes even if the edge connectivity is good, but if it is a poor vertex connectivity, then you cannot achieve much out of a particular network. So, we have to really see that both EC and VC, they become good. Now, some of the relationships, that VC should be less than equal to EC, EC should be less than minimum degree in the of the VI, not should be, it is found that it happens, and VC is also less than integer 2e by n, right. Why? Because just look at the degree. What is the degree? The total degree is 2e. So, what is the average degree? The average degree is 2e by n, right. Every vertex, the 2 edges are connected. So, total degree in the graph is 2e, and if there are n vertices, so if I make 2e by n with an integer, then we get that the vertex connectivity should be less than equal to. So, these are the relations we have, VC EC, then EC is less than minimum degree in a graph, and also finally we have seen VC equal to integer 2e by n. So, these are the theorems. So, these 3 theorems are there. We shall not bother too much about them, but we just look at this question: how will you maximize connectivity in a graph with 6 vertices and 12 edges? What will be its vertex and edge connectivity, right? So, you see, we have a graph where we have this much is only given. We have 6 vertices and 12 edges. Alright. So, basically the question is what VC and EC are achievable. So, this is the question, how much VC and EC we can achieve. So, here the E equal to 12 and N equal to 6, because 12 edges and 6 vertices. So, what is integer 2e by n? Integer 2e by n, it will be integer of 2 into 12 by 6. So, can you see that this is coming out to be 4, right. So, if it is say more than 4, then we have to take the integer portion and it will become 4. So, basically it says that it is possible to really achieve an EC and VC achievable is 4 only, right. And how many total degrees are available in the graph? Total degrees available 24, because 2 into 12. So, in the 6 different vertices we have to allocate them, and we have to see that each particular vertex should be having something like 4 edges. So, if this is a vertex V1, we should ensure that 4 things go out of them, and then like this we complete the design. Alright, and it therefore helps to really design a network by really creating the highest possible EC and VC if there are 6 vertices and let us say 6 cities to be connected by 12 roads. How do I make maximum connectivity? So, that is the kind of question we have addressed here, right. I stop here and we will continue the more about Cutsets and other concepts in our next lecture. So, thank you very much.